scalar, vector, and matrix are different types of mathematical objects that can represent different kinds of information. These entities form the building blocks of linear algebra, available us to understanding and solving a wide range of problems. But what exactly are vectors, matrices, and scalars? Let's begin with the scalars. Scalars are single numbers. They have magnitude but no direction. For example, the temperature of a room is a scalar. They can be positive or negative. Scalars in linear algebra represented by using Greek letters like lambda. Scalars are used to scale vectors and matrices. When you multiply a vector or a matrix by a scalar, each element in the vector or matrix is multiplied by that scalar. But vectors are list of numbers. They have both magnitude and direction. In linear algebra, vectors are typically represented with bold-faced letters, often accompanied by arrow above the letter. We can illustrate the motion of a car using a vector. Let's use a two-dimensional vector to show the movement of this car. With vectors, we can represent the direction and magnitude of motion of a car in measurable environment. The components of a vector represent the numerical values of the vector's magnitude in each coordinate direction. Each element in vector represents a scalar which shows how much and in what direction we should move forward. Now that we are familiar with vectors, we can get to know one of the most important vectors in linear algebra, the bases. We usually compare mathematical quantities to better understand them, and this comparison is usually done relative to a standard or a basis. In a very simple example, when we talk about a number like 5, we know that we can form this number by placing 5 units of the same kind together, the number 1. But what is the value of the number 1 in the real world? It can represent anything. Understanding this concept is very simple for us today. In linear algebra, basis vectors form the coordinate system. We are looking for an element that resembles the number 1 in coordinate systems. This means we can use it as a building block to create coordinate system and measure other vectors on that coordinate system. Let's start with one-dimensional coordinate system. Think of a car as an example. Our basis vector should have a magnitude so that we can easily scale it to the measure larger or smaller movement, much like the number 1. However, we know that vectors, in addition to magnitude, also have direction. Let's establish a convention. We will choose positive values on the coordinate axis as a default direction for the standard basis. Now, if we return to the example of car's motion, we can simply move forward by scaling the unit vector in the direction of the car's movement. This is where the importance of scalars become evident. But what about two-dimensional space? Here, a car's motion can occur in two different directions. So we need two unit vectors, each with a magnitude of 1, oriented according to our agreement. We'll name these two standard vectors I and j. Now we can represent any form of the car's displacement in these two-dimensional space using these two unit vectors. For example, for car's motion in a 2D space, where the car's displacement is 3 units along the x-axis and 2 units along the y-axis, as shown on the coordinate system, we should scale basis I 3 times and basis j 2 times. We can extend this to higher dimensions as well. For example, in 3-dimensional space, with 3 unit vectors I, j, and k, we can describe any 3D vectors. But as I mentioned before, we use bases to form coordinate system. We have established a standard for bases and have seen how we can represent vectors on the coordinate system created with these bases. But what happens if we change these standard bases? This is what we call transformation, or more specific, linear transformation. In a transformation, we change the magnitude or direction of the basis vectors and redefine the coordinate axis based on these new bases. Ultimately, we can represent all vectors we have from before in these transformed space. However, as we mentioned before, these transformations must be linear. In fact, we still need a Euclidean coordinate system after transformation, where the axes are orthogonal and coordinates are evenly spaced to each other. Let's examine this with previous example. Suppose in a 2-dimensional space, I change the basis vectors as follows. I set basis j to 1 and 1 and do not change vector I. Just change vector j. With these change, we redefine the coordinate system and we can reconstruct all vectors I have on the coordinate system based on this new coordinate system. We have changed our criteria for movement along coordinate axis and created a new coordinate axis. However, for a better understanding of what exactly happened to the coordinate axis and vectors, it's a good idea to have the previous shape of the coordinate axis in the picture. We usually don't show changes in coordinate axis in order to represent transformation. What matters to us is the changes that occur in the vectors after the transformation, and we focus on representing the transformed vectors. This is what happens in a transformation. Let's look at another example. This time, I set vector I as 1 and minus 1 and altered vector j to 1 and 1. With this change, we redefine the coordinate system once more, and we can reconstruct vectors 2 and minus 3 based on this new coordinate system. As previously mentioned, what matters to us is a transformed vector. So let's return to the standard coordinate system and see what is the coordination of transformed vector. When I return to the coordinate system with a standard basis, I observe that the vector 2 and minus 3 transforms into the point minus 1 and minus 5. So I've reconstructed my coordinate system and successfully transformed the vector into this updated coordinate system. Finally, let's unveil the matrix. Matrix is a rectangular array of numbers. They can have any number of rows and columns. So far, we have become familiar with the scalar numbers. We have seen that we use them to scale anything. Then we became familiar with vectors. We saw that vectors are formed by placing scalar numbers together. Each element of a vector used to scale the basis vector's element in a coordinate axis. Now matrices are also formed by placing scalar numbers together. However, we can think of these numbers as part of a vector. We can consider the vectors as column vector or row vector in a matrix. Finally, matrices are being composed of vectors placed side by side. For example, we can represent two vectors, I and j, which are the building blocks of our coordinate axis, side by side in a matrix. This is an extraordinary idea and opens up many opportunities in linear algebra. With this approach, we can consider each matrix as a building block that starts by creating coordinate axes and then define our vectors. Every time we define a matrix, we create a new measurable universe with its own unique properties and characteristics. And there you have it, the wondrous world of coordinate system in linear algebra.